In this video, we're going to take a look at what are called higher derivatives. Mainly that means derivatives further than the first or second derivative. And most of the time, you won't need to go past the second derivative, but there may be times that you will. Today we're just going to look at it more for like a creative math venture, and even to look at patterns. So you'll see some tricks coming out here a little bit. First of all, I just wanted to show you some of the notation here. For a function, if the function is y, then the first derivative would be y prime, y double prime, y triple prime, and then here's how we look at the fourth derivative. It almost looks like an exponent, but it's not. It's just notation. Same thing goes for a function f of x, first derivative, etc. Here is more of like the what we might use with implicit differentiation, some of the notation here. And lastly, just more maybe more terminology here. If your function represents position, then the first derivative represents velocity and the second derivative represents acceleration. And I guess you could go a step further, and there's the third derivative of this is called jerk. All right, you can look that up if you want. But we're just here to have a little fun with this. This question, you probably won't even see this notation much at all, but it means find the 35th derivative of this product right here. Okay, so 35th derivative. So let's see, if we talk about the first derivative, we're going to use the product rule. So first derivative of the second plus second derivative of the first. Second derivative here. So I'm going to circle that. Product rule here, and just a sign function here. So product rule. First times the derivative of the second plus second times derivative of the first plus the derivative of this, which is cosine. So if we simplify this, we get negative x sine x plus 2 cosine x. I'm going to circle that one for our second derivative. Third derivative. Product rule. First derivative of the second plus second derivative of the first plus the derivative of that, which is negative 2 sine x. Simplify, and we get negative x cosine x minus 3 sine x. 4. Here we go. You don't have to stop the video because this is going to take forever. We're actually not going to do this out 35 times. What we're actually going to do is we'll begin seeing a little bit of a pattern emerge here, and we'll be able to predict what this 35th derivative is. A couple more here, maybe 3 more. All right. I'm actually going to pause the video right here and write out the rest of them, and we'll talk about it. That'll save some time. Okay, continuing the video here. Notice what I've done. I've gone out to the 6th derivative. That's definitely a higher derivative, but we're still looking for the 35th derivative. Okay, you could sit here and go through all this, but I want there's a pattern that's kind of emerging here. I want you to notice that it cycles through every 4 derivatives. So notice how here we have x cosine, x sine, x cos. So the sines and cosines alternate here, as well as the sines and cosines in this column. Notice the signs, meaning the S-I-G-N-S, pluses and minuses, plus plus, minus plus, minus minus, plus minus. And then look right here where the 5th derivative matches up with the first derivative. The only difference here is that this number out front. Notice though that this number is the same as the derivative. So on the first derivative, this number was a 1, second derivative 2. Okay, so we can fairly quickly, and maybe you can pause it now and make a prediction about what this will be. But go ahead, yeah, pause it. Every multiple of 4 ends up right here. Think about it. It would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so you could say 32 is a multiple of 4. 32 would end up right here. 33, 34, 35. So this is the form that we're going to be looking at. Or you could say 36. That's a multiple of 4 would be here. 1 back from that, 35. The only adjustment we have to make here is this number seems to be the same as the derivative that we're taking. So that would be negative x cosine x minus 35 sine of x. That is definitely a time saver instead of taking this out to the 35th power. So kind of fun, looking at patterns, some creative problem solving here. Same thing goes with this one. A little different. This time they want a formula for the nth derivative. Okay, so we're going to again create a little pattern here, and let's maybe look at this as so we can use the power rule and the chain rule here. So the first derivative, f prime of x, is going to be negative 1 times 5x minus 1 to the negative second power times 5. All right, because we're looking for a pattern, I am not going to be multiplying this times this. You'll even see in the next step, I'm going to do something different on that one. The second derivative is going to be bring this negative 2 down. I'm going to actually keep that negative 2 separate from the negative 1. 5x minus 1, here's our power rule, followed by the chain rule. So there's going to be another 5 multiplied out here. Again, I'm going to pause the video and allow you to maybe write some of these steps down and see what you can do, and we'll be back. Okay, we're back. I've written down just the first 4 derivatives, and we can definitely see a pattern emerging. This was a little bit of a faster process. Now we're going to come up with a formula in terms of n here that represents the derivative that we're on. So there's actually 4 things going on here. Well, let's talk about this one first. I think it's the easiest. So in each of these steps, this quantity is always 5x minus 1, and notice that the derivative value is negative, and it's 1 more than the derivative we're on. So on the first derivative, that was a negative 2. On the second derivative, negative 3. So we can talk about that as negative 1 more than the derivative. So negative the quantity n plus 1. You could also write negative n minus 1 if you wanted to. Probably the next easiest one would be this list of 5 here. Okay? Notice that the number of 5s that are being multiplied correspond to the derivative that we're on. So we can say here, well, we know on the nth derivative there will be n 5s being multiplied together, so 5 to the nth power. Next thing, notice on the first derivative 1, then we have 2 times 1, 3 times 2 times 1, fourth derivative 4 times 3 times 2 times 1. That, some of you might be aware of that, a lot of you might be aware of that. That's a factorial. That would be, take the derivative, so 4, 3, 2, 1 is 4 factorial. 3, 2, 1 is 3 factorial. Okay, so this would be n factorial. And you might have been wondering, well, what about the signs of this, the pluses and minuses? Notice that we start with a negative, and then 2 negatives here make a positive. So this would be a positive, negative, positive. So we have to come up with something that would alternate the positives and negatives. And this is what does that. When we're on the first derivative, that's negative. When we're on the second derivative, that would be negative 1 squared, which would be positive, and this would allow the alternating of positives and negatives. So here is our answer for the 5th derivative. I'm not going to show this, but several years ago I had a student say, well, we found the nth derivative of this. Why did we only find the 35th derivative of this? What's the nth derivative? I'll tell you, it's a pretty crazy process, but it's a good challenge for you. Try it out.